Okay, the recording is started. Good evening, everyone. Good evening, sir. Welcome back to session 2 of day 5 Faculty Development Program. Our keynote speaker for today's event is Dr. T.P. Sharma. He is Associate Professor at NIT Hamirpur, and he has around experience of more than 28 years in academic field, and he is presently head computer center at NIT Hamirpur, and he holds a PhD degree from IIT Roorkee, and his specialization is in fault tolerance and energy efficiency in distributed systems, wireless sensor networks, MANETs, VANETs, IoTs. He has over 120 plus research publications, and he has broad international exposure, serving on conference committees worldwide. Professor Sharma has supervised 6 PhD theses, and more are in pipeline, and over 60 MTech theses. He has managed various research and development programs and held roles such as head computer centers, associated deans, research and consultancy at NIT Hamirpur. And previously, he also offered his services as assistant director and deputy director at Himachal Pradesh Electricity Regulatory Commission, Simla. So welcome again, sir. You will be taking topic on concurrency and synchronization issues in IoT and WSN. Beside being good at academics, he is also an livid sports person. And congratulations, sir, for just winning, for being runner-up at the Inter-NIT cricket tournament and ongoing badminton tournament at Kurukshetra. All the very best for it. So today he will be taking challenges of managing concurrency and synchronization in IoT and WSN, focusing on ensuring efficient communication, data consistency, and coordination among multiple devices in real-time environments. So I'll not be taking much time, so I hand over this platform to Dr. Sharma.
Thank you, Dr. Viva. First of all, thank you very much. I would like to thank Directorate of Technical Education, the whole department, the Principal Government Polytechnic, and obviously the coordinator, Engineer Pankaj Thakur, and Dr. Viva Sharma, who has invited me to give a talk to this beautiful course that they have designed. And also, thanks for mentioning my special interest, that is actually sports also. So presently also I'm delivering my lecture from my friend's cabin at NIT Kurukshetra. Pardon me if there are issues in connectivity or something. Please let me know through message or something if there are any issues in audio or video. I suppose everything is fine before I load my presentation.
Yes, sir.
Right, then it's all right. Let me just upload my presentation here. Just one sec. I'll be Chrome tab, Windows, that screen. I will see it in the controls.
I think now you're audible.
Is my presentation visible?
Yes.
Yes, sir.
Right. So everything is fine, I suppose. Right. Is my presentation visible in a full mode?
Sir.
Hello?
You are only visible,
right.
sir.
I'm visible. Screen is not visible?
Screen is not visible.
Visible, sir. Visible.
Yeah, everything is visible,
It's
sir.
visible, but
It's visible, sir.
Everything is okay, sir. It's visible, sir.
No issue.
So the blackboard and yourself are visible, but screen.
Please let me know that that's what I am confirming whether it is visible to. Just one
Exit
second.
and enter full
Sir,
screen.
it is your visual.
Visible, sir. Everything is visible. You are also visible and screen is also visible.
Right.
And it's in presentation mode as well.
Okay, good. That's good. Looking into the audience mix, what I have done is, though my presentation is on concurrency issues in distributed systems and everything, so keeping the interest of everybody's in mind, I have designed my presentation in a way that everybody takes out of this presentation something of their interest, his or her interest. So basically, let me start with a distributed system. Then we talk about IoTs. You might be hearing nowadays a lot of jargon of these technologies where we talk about wireless networks, wireless sensor networks, IoTs, cloud computing, everything. So if we understand, all these are nothing but are the distributed systems in the background. So before understanding what are the research challenges, especially to the synchronization issues, or what are the research challenges in these, when we talk about WANets, when we talk about IoTs, other type of issues, we have to understand that what actually is a distributed system. Unless and until we understand the distributed system, we cannot appreciate and understand what are the research challenges over there in distributed system. So let me make it very simple. You can see all around many definitions of a distributed system, but definitions apart, let us start with a very simple discussion of multiprocessor systems. All of you understand that you have a single processor system, you have a multiple processor systems. So in a single processor system, all of you understand on your board, you have a one powerful processor and that does everything. Associated with your processor, you have multiple, you can have associated memories, you can have associated other kind of registers, pool, or all those kind of devices, all those kind of components over there. Okay. So what happens if I want to run more than one processes on my system? So there are concepts of multi-programming, multi-processing, multitasking. So all these technologies, all these terminology have evolved over the time when these computing devices have evolved. Okay. So all of you understand, if you know, if you take a process and if you analyze it, you find that 80 to 90% of time, your processor is not occupied in computing. So that is called, if you take a complete track or execution track of any process, you find 80% of the time your processor is free. Whereas at the same time, you understand that the processor is the costliest resource in your computing device. So how to utilize this? There came a concept of multi-programming, there came a concept of time sharing. So I'll not take much time in that, because in order to understand what actually is a distributed system, then how all these technologies are linked to this concept of distributed system, we have to understand that if you have a multi-programming environment, so what happens in a multi-programming environment? You have a single processor, but we create pool of processes, okay? And pool of processes take turns to execute on the processor. And how they take turn? So they can take turn, either you fix a particular slot. So if one process goes into your processor, then it goes to a wait list, then another process goes, then so it could be preemptive or it could be non-preemptive. All of you might be understanding. So I'm not taking much time. So the gist is, in order to increase or maximize the processor utilization, we have the concepts of time sharing and multiprocessing. But as the technology grew, what happened? That the computational requirements also increased manifold. So what was thought, that if you run something on a single device, can be split it into multiple jobs, like we do it in time sharing and multi-programming. A big job is converted into smaller processes, and these smaller processes are run in parallel concurrently. In parallel in the sense, logically they are parallel. But if you think in terms of a hardware pace, if your processor is a hardware, so all these whole processes will take turn internally, and scheduling will be done internally by the system without the intervention of the user. So to a layman, to an outsider, it appears as if multiple processes are running concurrently. Whereas there also there is a sequence, but this sequence is driven and followed by what you are following. Either you are following a fixed time quantum or you are following preemption policy. But if you separate these processes further apart, now your processors, you can have multiple processors on the same board. Think of another situation. You have multiple processors on the same board. Now you can run multiple processes on these two processors. If you have two processors, you can run processor one, processes one, process two, process three on one processor. You can run process three, process four, process five on another processor. So you can create like this. But if you separate out these processors, that means you have multiple machines. You have one device, you have another device. So every device is having its own memory, own communication buses, and everything. Okay, so even if you have multi-processor systems, they also run multiple processes in parallel. But entire internal communication is through internal buses. If process P1 and process P2 are running on the same machine, they are sharing same clock. They are driven by the same clock. But if process P1 is running on one machine, process P2 is running on another machine, still they need to coordinate. There must be synchronization. But the issue is now they are connected through the link. They are connected through the network. When you have two processors on the same board, delays are in terms of nanoseconds. So, and they have the same clock. But when you have multiple processors on separate machines and you run processes concurrently, so if they want to coordinate, the delays through the network are in terms of millisecond, and there is an issue. So in a simple language, we define a distributed system, a kind of system where you have computing devices which are running processes. They want to communicate with each other, but their interconnection is through networks. So that is a big thing. And you understand, if one process is running on one machine, another process is running on another machine, and each machine is having its own clock, no two clocks can remain synchronized forever. So there comes synchronization issues. So making it further simple, there are so many definitions, so I'll not go into this. I have made it clear. Now you think of a situation like this. You have machine A, machine B, machine C. When we say machine A, machine B, machine C, obviously it means a computing device A, computing device B, computing device C. So everything, you have a local operating system in each and every machine. And there is a special type of layer, which is very important, which we call it as a middleware layer. We will touch it later on. Middleware is a kind of layer which manages so many things. For example, as we are saying, we connect multiple machines together. Say in one of the computers, you have Windows operating system. In another, you have a Linux operating system. In another machine, you have some other Solaris or some other kind of operating systems. So you have different kind of operating system. You can have even formatting heterogeneity. Like in one of the system, you are storing data in a different format. In another system, you are storing data in a different format. When I say different format, like for example, all of you understand, you have a byte. You want to store it in a memory. So will you store it at a first place, the MSB or the LSB? So depending upon whether you store MSB, then the next bit, then the next bit, or you store first the LSB or the next bit. So these representations or these formats are called big endian or little endian. So many machines follow big endian, many machines follow little endian. Suppose now machine A sends some data to machine B, and machine A's recording and the storing and communication format is big endian, whereas your machine B is for having a little endian format. So there is a heterogeneity. The interpretation of the data will be wrong. So there are many layers in between, and the special mention is the middleware layer, which does all these kind of transformations, all these kind of fixing. There are various kind of services which middleware layer provides. So that we will try to touch the services of the middlewares also. So on top of that, when you bridge all those kind of heterogeneities, on top of that, then you can run distributed applications. Don't worry, we'll take all those services, all those different kind of heterogeneities in detail in the slides to come. So obviously, there was a time when these networks evolved. At that point of time, we used to ask, what are the advantages of networking? So if you talk of what are the advantages of networking, exactly same are the advantages of your distributed system. You can share resources, we can have communication, we can have, it is an inherent distribution where you can distribute your computing tasks. Speed Something is done by one machine. Now you are splitting that job into 5 different processes, and you're running concurrently on 5 different machines. So obviously speed, economy, because if you want to scale up, okay, if you want to run it, you have now a computing requirement. You have now a job which cannot be run on your this machine. So definitely you will have to buy another machine. But no, if you are following this distributed system regime, you can add another system, existing system, and you can split the job. You can run concurrently, so you achieve economy also. So that is also the incremental growth. Reliability, it is a very, very important characteristic of distributed system, which we will discuss time and again in the coming slides. Reliability, simple words I'll say, you are sensing a particular environment, you deploy a big powerful sensor. You can do the same job if you deploy there 10 sensors, maybe of some smaller capacity, some cheaper 10 sensors, but they do the same job. Which system will be more rugged? Which system will be more fault tolerant? Obviously the second one. Suppose if one of the sensor goes down, still nine sensors are working. 2 sensors goes down, still your system is working. But if you have one system, one big sensor, it goes down, entire sensing paradigm goes down, right? So obviously these are the advantages. Now this is very, very important for the researchers, those who are doing their MTechs, or those who want to do PhD, or those who want to understand actually what is a distributed system. I divide it into these 3 categories. One is the concurrency, next is lack of global clock, and next is independent failure. Now try to understand this, and this will give you so many hints. As I told you, you can have multiple processors on the same board, same machine. They can also run multiple processes, but their internal communication is through internal databases, internal address buses, internal same clock, right? But when you split it apart, that means you are running now your processor on different machines. So there are obviously concurrency issues. As I told you, every system, every computing device has its own clock. They are running, suppose, a logic which says that let us do this particular action at 10:30 a.m. Now, both initiate the same action at 10:30 a.m. That is their own time which they are running. But obviously, if we see from an independent frame, there might be some skew. There might be some offset in time if they are not synchronized. So one on an actual frame might be running 10:30, another might be running 10:31 or 10:32, something. So their action will never be synchronized. How to solve this problem? See, today's internet, we have so many machines and still we do so many transactions. If you're a banking organization which specifically deals with thousands or millions of instructions, millions of these transactions every day. So, but they do not run on a single system. They have multiple servers, multiple clients, multiple these things. But how then these actions are actually synchronized? This is a big issue. So be it IoT. Now think of your IoT. You have designed your IoT, for example, you have put certain sensors in certain devices, and then you are collaboratively performing certain tasks. But every component, every device is having its own clock. So it is running its own time. So how do you actually basically synchronize this? So synchronization and coordination in itself is a big, big research issue. It has been a big research issue for many, many years, and still it is a challenge, right? So it stems from lack of global clock. Think of a situation that if there is a notion, there is a procedure where you have a single global clock and which provides time to every system all the time, then problem of synchronization will be solved, but it is not possible. You might be thinking that on your devices which are connected to the internet, you will find that they will be synchronized, they will be given time, and they will be running certain time. And how many of you know that what is the name of that protocol? Can somebody answer? What is the name of the protocol on internet which coordinates this time, which synchronizes time? Anyone? The name of the protocol is NTP, Network Time Protocol. Okay. So what happens is this time which all the devices on the internet are connected, they are synchronized. They are synchronized through a protocol which is called as NTP. There is no global clock, but there is a certain mechanism through which periodically, after some time, we synchronize. If there is a drift, there is an offset in time, we try to cancel it out. We try to fix this, and we try to keep the time of different clocks as close as possible, right? And the most important, apart from this concurrency and global clock issues, is the independent failure. Now, I was talking about the reliability. In a distributed system, you distribute the system as the name indicates. You do not run it as a centralized system. Do not run as a single unit. You distribute it. So it has got its own advantages, right? It increases the ruggedness. It increases the fault tolerance. But at the same time, there is a very peculiar thing that it exhibits a characteristic which is called as an independent failure. What does that mean? If you have a one log of wood, single wood piece, thick piece, okay, if you throw it, if you turn it, if you flip it, it flips, okay? Or other way around, I want to explain it. If you are independent, if 5 devices are independent, by independent I mean they have their own clock, they have their own memory, they have their own processor, they have everything on, and these systems are running concurrently. If one of the systems somehow goes down, if the one of the system goes down, it is not immediately known to other devices. Other devices will keep on doing their normal work until and unless the point where they wanted to talk to this particular machine. If they want to have some communication with this particular machine and it is not responding, at that point of time, other machines will come to know that machine number 5 is down. This is called as independent failure. This has got advantages and also disadvantages. For example, let me make it simple. You are running 3 jobs, 3 processes on 3 different machines. Process 1, process 2, process 3. Process P1 and P2 are executing. Somehow P3 goes down. And these are very long processes. P1 and P2 still continues to execute, continues to run, continues to do processing, till the time one of the process wanted to send some data to the process P3 or wanted to consume some data from process P3, and it is not able to do that. So that means at that point of time, it has come to know that process P3 has failed. What happens to the fate of the entire execution that P1 and P2 has taken place? So P1 and P2 was executed. Had this P1 and P2 come to know about the failure as early as possible, they would have not executed. They would have cancelled their execution. So independent failure is an advantage, and it is also a big disadvantage. So there are many schemes, many things, many researches have been done over there, how to timely detect failure. If your failures are independent, why failure are independent? Think of a situation. If there are 2 logs or 2 pieces of some metal or wood, they are just balanced with each other. If you flip one of them, the other will also fall down because they are dependent. They are dependent on each other. But if you have something which are independent, if something happens to one piece, will not be immediately known to the other one. So it provides fault tolerance, but it is also a disadvantage. So a lot of research is going on this. Now think of a situation of an IoT, because this course is typically talks about IoT. So what IoTs are? IoTs are independent devices which you can have a microwave, you can have a fridge, you can have a watch, you can have a sensor board, you can have anything. Okay, now they can fail independently, and if their failures are not known for a longer period of time, you can face so many consequences, right? So nowadays, what are the example of distributed system? Heterogeneous network of computers, like for example, internet. The biggest example of distributed system is your internet, right? So you can have a distributed multimedia, like there are specific networks, a kind of networks like internet. Let me make one thing here clear. Many times, many students, including MTech students, PhD students, BTech students, do not understand the difference between the internet and the internet. So you might be thinking what he's talking about, the difference between the internet and the internet. You might have read many times while studying computer networks the term internet. If in a particular sentence in between, it is not the first word in your sentence, then obviously first I will be capital. If that's not the case, if you think of internet written in a particular sentence, if your I is small sometimes and I is capital, there is a huge difference. Try to understand this. Internet, everybody understand? In general, if you talk about in general internet, so internet is nothing but collection of many networks. So it is generic term, collection of many networks. So if you create many collection of these kind of networks, they will have some name XYZ. Okay, you can name some of the networks as XY, some of the network as ZA, something like exactly in a similar manner. The name of the internet that we use nowadays, which is a TCP/IP based network, its name is internet. Try to understand it. Its name is internet. If you talk about internet whose name is internet with capital I, so it means we are talking about a network which we are nowadays are using, which is basically primarily a TCP/IP based network. But when we use a term internet with a small I, that means we are talking about any network which is a collection of many networks. Is it clear? So make it very, very clear while you study network, text, books, and you write papers. We write text without understanding this particular difference. Intranet, if you are an organization, if you are an industry, if you are anything, so you might be having some set of say 50, 100,000 systems within your organization, and you all are interconnected. That's also an example of your distributed systems. Likewise, mobile and ubiquitous computing, this is another example. Okay, so you have devices, you go to a hotel, you go to a restaurant, you go to airport, you go to bus stand, anywhere you go, whatever devices you carry with you get connected to the existing network. So you can fetch the services from there, or if your device is having certain information, you can offer it, you can share it so that others can use. So obviously this is called as a spontaneous networking also, mobile and ubiquitous computing. You go to a network and you fetch. This is another example of a distributed system. So more importantly, let us come then what are the challenges? Try to understand this. What are the challenges then in this distributed system? Be it IoT, WAN, wireless sensor network, clouds, everything. So first thing is heterogeneity, then openness, security, scalability, failure handling, concurrency, and transparency. Let us see one by one. Sorry. Let us see what is heterogeneity. As I told you, networks. There could be different kind of networks. Internet, again, I'm talking about internet, today's internet, capital I, our internet. It is also a collection of many networks. Some networks might be running different protocols, another network might be running different kind of protocols. Some might be having a different MTU. All of you might be understanding what is MTU, maximum transfer unit. So you know, some networks, if you're passing, making it simple, if you are passing a packet of particular size through internet, there might be intermittently certain networks whose maximum limit of passing a packet is small, whose MTU is small. So obviously what we need fragmentation. We want to fragment it, this particular packet. At another end, we do defragmentation, where we again combine all these packets and form the original packets. So this is in terms of the MTU. Likewise, different protocols. As I told you, computer hardware. One of the manufacturer having a different architecture, another is having a different architecture. So one is having a different data representation, another is having a different data storage representations. Likewise, operating system. One system is having Windows operating system, another is like a Linux, another is actually. Still, you want to interconnect them, but how they will talk? How they will talk? How you will bridge this heterogeneity? This is the big challenge. Programming languages. One is having a Java platform, another is having some other platform, another is having some other platform. Even if one is you are running certain compiler, there might be differences in compiler also. There might be differences in right. All right. Thank you. There might be differences in compilers also, right? So as I told you earlier, who comes to rescue? It is a middleware. Very, very important. Those who want to study, those who want to understand, those who want to have a topic for their group discussions, for their seminars, for this. So studying and understanding middleware is a very, very good topic. So it covers all these heterogeneities. One of the oldest example is Corba. I don't know how many of you hear this. COM, Microsoft COM, DCOM, Corba. And there are new, modern, new middleware. So I'm just putting it forward for the audience to study it, to go through this and study their architecture, how they do it, and what are various kind of services that are offered by the middleware. Okay. Second is openness, very important. I'll compare. I'll take two very related and interesting things, which is these are openness and scalability. Before I go to openness, let us see scalability. All of us, all of the audience might have heard this term many number of times. System must be scalable. Scalability. What is basically scalability? Scalability is you have designed a system for a particular number of users, right? Now, number of users increases. Now your number of users are increasing, What do you do to cater? Still, you want to provide services to those users, so you can add new resources. Further, your user increase, you can add your resources. But if your system is not designed properly, as you add more users, as you load more resources, the performance of the system will dip down. And also, the cost of adding these resources will increase. So we call a system scalable if we have designed this system in such a manner that if the load increases, if the number of user increases, we can add it and it does not have any significant impact on the overall performance of the system. And also, the addition of new resources does not take much effort or much cost. So, in a pure term, we can define scalability is the capability of any system to cater to the increased load without incurring much cost and effort. Then you can call system. Suppose, for example, another way I tell you, you have a server, you were catering 5,000 users. Your user increases to say 6,000, 7,000. And your overall performance of the system dips down to below a threshold. You have no other option than to buy another server, which is very costly, and put it there, and then connect these two servers and provide the services. But if you have a kind of server where you can add some more to the existing system, you can add some co-processors, you can add some cards, you can do something, then you can say that your system architecture is basically scalable. So in a pure term, I tell you, scalability is the capability of any system to cater to the increased load without much effort and cost. Then you say this is a system scalable. Then what is, let me come back to openness. These two terms are many times confused. What is then openness? Openness is basically in terms of functionality. When you design a system, this system could be any software system, any mechanical system, any electrical system, any system you take any system. When we say the system is open, what does this mean? This means in terms of functionality, you have certain set of functionality in a given system, and you want to add more functionality into this particular system. And your system is designed in such a manner that with very ease, comfortably you can add new features, new capacities, new kind of functions into your system. Then you say the system is open. And how this is possible? For example, if you have designed your system, I am typically talking about the software system, the computing system. If you have designed your entire module, entire system in such a manner, in a layered manner, in a modular manner, you have a one module, another module, this module, one module provides services to this module provides to this services. Then if you want to change something, if you want to add some functionality, you modify only one module. You need not to modify other module. Then you can say you have an ease of modification. Another thing, one team has actually designed a particular system with all its wisdom in a particular manner, and they have not maintained any modularity fundamentals. They have not maintained any standard procedures for naming the variables. They have not put any appropriate comments in their entire code, and so many things. So now if new team comes and want to modify it and to add some new functionality into it, can it do it? No, they will have a lot of problems in doing that. So you will say your system is not open. Another example to make it clear is, for example, nowadays you go to the market, you buy a pen drive, you buy a memory stick. Do you ever bother if I am buying this memory stick, will be there some interface problems or not? If I connect it to my laptop device or my desktop, will it be connected or not? We never bother about this. Vice versa, if you are buying a device Do you bother that in future I'm going to use all these peripheral devices, whether they will be compatible this or not? Why this is not open? Because all are following open standards. All are following open USB standards. So that means your system is open if your functionalities, your standard interfaces are publicized. They are made public. They are known to everybody. Then you are following open standard. So openness is in terms of functionality. Scalability is in terms of number of users, load. Okay. So saying is very simple, but you are designing a system, IoT system, a distributed system, any kind of system, and you want to have these two properties. And you are actually the team, you are actually the designers who want to include these properties into your system. So how do you do this? That is actually the engineering. That is actually the research. How do you make your system open? How do you make your system scalable? Okay. So that is there, openness. And security, next challenge is security. And incidentally, you might be hearing there is not much to say about why security is a challenge and why it becomes more prominent in distributed system. You have only one unit of anything you keep in your palm, it is safe. You have 10 of it, you cannot hold it in your palm, you place it here and here and here. Somebody can steal it, somebody can destroy it. Still, you distribute it in many places, there are security challenges. But at the same time, somebody says that my system is secure if I do not use it. So if you do not use it, so you cannot say that your system is secure. That's why I tell you, if you see the three terms over there, confidentiality, integrity, availability. This availability term is added into security very, very integrally. If you do not make your system available, you want to make it safe. I want to keep it safe. I want to keep it safe. So I will not make it available. So there is no use of such kind of security. You will have to make your system secure. At the same time, you will have to make this system available. Like, so three dimensions of your security is confidentiality. If I'm sending something, it should not be read by somebody else. It should not be altered by some. It should not be read by something else, or it should not be. I mean to say, there should not be a man in the middle kind of attacks. Then we say our system is confidential. Integrity. It should not be altered by anybody. Nobody can alter it. Then you say whatever is sent is actually received. In case of confidentiality, nobody will alter it, but will read it. Then we say its system is not confidential. But at the same time, if you are having confidentiality and integrity, you will have to make system available also. Okay, so that's why there are concept of there are specific attacks on this availability. You might have heard about denial of service attacks, distributed denial of service attacks. So security in itself in a distributed system is a big challenge, especially for IoTs. I tell you, and the example all of you have seen in Lebanon, what happened? What happened to the pages? What happened to the this? So those devices were also connected. They have sensors, they have communication capabilities, they have everything. So likewise, tomorrow you have mobile in your pocket, you have all the devices, your lights, your fridge, your refrigerator, your microwave, your watch, everything connected to the internet. And also these devices are having sensors. They are also having computing capabilities. So everything can be controlled. To some extent, to the large extent, to a small extent, but they can be controlled. So security, providing security in IoTs as well as a whole in a distributed system is a big challenge, right? Scalability we have already talked about. So one of the example of scalability, simple example is like IPv4. All of you understand IPv4 was a 32-bit header. Okay, all of you know it's a 32-bit xxx.xxx.xxx. You know IP addressing. Okay, so in IP addressing in IPv4, it's a 32-bit, and you understand that at point of time when it was designed, it was never thought that it will ever exhaust. These many of IP addresses assigned to global IP as a global IP to the devices connected to the internet, they will never exhaust. It was thought, but what happened? This is the only reason that we have to go to IPv6, right? There is another example. I don't know how many of you have heard about Y2K problem. There was a very famous Y2K problem. And when I was actually, I joined this NIT Hamirpur in 96. So around 99, the entire CSC class in 2000 flew to US. They got job offers from US. And the only issue was to solve a very small problem, which is called as a Y2K problem. This again is related to scalability. So what that Y2K problem was? Can anybody explain? Have some idea about Y2K problem, or heard about Y2K?
Yes, sir. The year was a 2-digit only.
Yeah, yeah.
Yeah,
This was a very
2 digit
simple
year.
problem. That, exactly. So when they designed, they have written a date format at many places. They have kept only 2 places for year, YY, right? So when it was 9999, so next year will be 00. And there were in many embedded programs, any soft and many programs written in a soft form, many programs written as embedded programs in many devices, including your airplanes, including in your metros, including your so many devices, wherever you have embedded devices and a micro program devices. So if there were certain date functions written over there, if you do some computation based upon date, the current year minus this year divided by this, there used to be many kind of errors, stack overflow, this overflow, wrong, negative value, this value, everything. And it was hoped, it was imagined that the systems will collapse. Every system, every banking system will collapse. Forget about the banking system, aeroplane, jets, everything. Wherever you have embedded system and you have put some date functions over there, so everything will collapse. So what will happen? Only thing was to change the year format from II from a 2 to 4. So again, because people never thought that we will reach at a 999 and there will be a problem. So this is again a scalability problem. A failure handling, very important. And my PhD, while I was doing my PhD from IIT Roorkee, I was working upon at long back in 2005 onwards on data aggregation, data collection, energy efficiency, as well as the fault detection in case of wireless sensor networks, right? So as I told you, detecting failures in distributed systems are challenging. Why? Because they are challenging because failures are independent. Now try to understand this. Why it's a challenge? Because failures are independent. If failures are not independent, these failures will be immediately known. So how to detect those failure detectors? And those failure detectors must be reliable. So designing reliable failure detectors are very, very important. And also I want to tell you that those who want to do further research and study, there are election protocols, there are coordination protocols, there are synchronization protocols, right? And all these protocols are designed in such a manner that you want to have some consensus. There are 20 systems, they have sensed something, and they want to finalize whether there is an enemy in the battlefield or not. 5 sensors says something, no. 15 says yes. Should we conclude finally that there is an enemy? Or if 2 says no, 18 says yes, then should we conclude, is there any limit? So I tell you, there is a specific work done, very deep research done on this, that if you have n number of systems, and if this many number of systems fail, still remaining n minus f systems are able to take correct decisions. So how do you find that f? What should we, if you have 100 systems working collaboratively, how many systems you can allow to fail despite the fact you can still take a correct decision? So what should be that limit? So a lot of people have worked on that. You can find this on the net. There is one author which is called a Dolev, Dolev. I do not remember the year, but if you find Dolev, then you write a failure, number of failures, or some these keys on the Google or somewhere, you will find many papers on that. Okay, so despite the fact they fail, then how to work on that? Like there are Byzantine failures, there are there's many kind of failures over there, crash failure, process failure, communication failure. What kind of failures are there, and how many failures you can allow, and how you can do this? Okay, so detecting failures are very, very important. So if you want to, as a end user, to a worker, to a user, if you want to mask failure, and the first strategy for any running system to deal with failure is tolerating the failure. I tell you, tolerating the failure. Somebody says, what is the best method to deal with the failure? You will be surprised that best method to deal with the failure is to tolerate the failure. Think of a financial organization running millions of transactions worth rupees of millions and trillions. daily. You can imagine per second. You can imagine per microsecond. So if something goes down, should the company shut down the servers for 15 minutes, half an hour, and do the recovery, then again restart? Or if still, despite those failure, performance is still manageable, performance is above a threshold, company will never allow the system to entirely shut down. So it will tolerate. So best method to deal with the failure is basically tolerating failure up to a certain limit, right? So, and how do we mask the failures? Mask the failure means failures are there, but still we want to mask them internally. As you might have studied, those who are computer students, those who have study various protocols, sliding window protocol, this protocol, this protocol. There are many protocols at the transport layer. There are many protocols at the data link layer. Okay, you know, you understand that errors in a particular communication paradigm, when it is in networking, are handled both at the data link layer as well as the transport layer. So how they do internally, if there are certain frames which are lost, automatically retransmissions are done. So retransmission is a method which is used for the masking. There is another method of how we can achieve masking, that is redundancy, redundant storage. Suppose, for example, you have one hard disk. Instead, you have two hard disks. They are strongly linked to each other. You are doing mirroring, or you're doing stripping, or you're doing some kind of management where you are creating shadows, you are creating images, or you are doing stripping or something. So you have redundancy. If one of your storage goes down, it has failed, but still you do not have that impact because another its image, its storage is working. At the same time, you can do some correction, right? So these are the methods of masking, that is retransmissions and redundancy. Okay. Another way, if you want to, you might be knowing that recovery from a failure, how do we do? If you want to recover it, you will have to do rollback. A lot of work is there on this rollbacking also. Think of a situation, you're doing transactions on an ATM. Okay, now ATM are also your IoTs. This is another example of IoTs. We sense many things, your face, your this thing, your ATM card, your this thing and everything. You might have seen and felt that many times your transactions is stuck in between. You have put certain things, certain these things. And let me make first clear, there are many confusion among students and researchers. What is the difference between a operation and a transaction? What is the difference between operation and a transaction? Operation is a single atomic action. If you bundle similar actions together, many, more than one actions together, similar, which result into some big task, we call this as a transaction. Like you go to an ATM, you punch your card, so your card is read, it is sent somewhere where the detail of whole card is there, it is authenticated over there, then it goes to your banking server, it checks your balance, it goes to a server where there is a balance, then it goes to another thing which you put a value over there, then it checks whether the remaining amount your bank is beyond limit or above limit, this thing, that thing. So many things are there. Until and unless you get the finally cash in your hand and you eject your card out of this, all are related actions. So you call it as a transaction. So if you're performing transactions and there are in between certain failures, what we do to deal with this? We have to roll back. We have to roll back. That means undo these actions to a certain point. Until that point, if you have done the changes permanently, then still you can forward, or you will have to roll back to the initial point. So recovery from failures is rollback, redundancy, availability, right? Concurrency. Now that was the topic. Why concurrency? Because you are running concurrently so many things. You cannot synchronize. You cannot keep clocks of all devices which are autonomous synchronized. Even if, think of a situation, you are in a class, you are a teacher, and you are teaching your class of 1,000 students, 500 students, those who are sitting in a particular hall. Can you imagine that when you are saying something, all audience, all students are not hearing you exactly at the same time? There is a delay. Same is the case with, you might be thinking, what is the issue in time synchronization? There is a one machine which is a time server. It broadcasts, it sends time to all the machines hear it and set time accordingly. After some time it again sends time, they will hear it, devices will synchronize. It is not as simple as that. There are so many protocols, so many research over this. How do we synchronize these software clocks, these hardware clocks. So there is a Christian's algorithm, there is a Berkeley algorithm, there is a NTP algorithm. There are so many algorithms. But later on, also it was thought that, interestingly, that it is not possible to synchronize hardware clocks all the time. So Lampert is one of the very famous researchers who came up with a notion which is called as a logical clocks. Many of you might have heard, many of you might not have heard. Logical clocks. They have nothing to do with, they are not calibrated to our time. They do not talk about 10 hour, 20 minutes, this minute, or this time, or this time, or this time. The time is very simple, 1, 2, 3, 4. It's a counting, but it is not related to your real time. It's related to events. If two processes start from 0, 0, if one event occurs, their clock goes to 1. Another event occurs after some time, it goes to 2, and so forth. But then how it is related, then how it works, and how it solves problem, this is again a very, very interesting thing. And I recommend to the researchers, I recommend to the audience, those who wanted to work and those who are working in the area of synchronization, that without understanding the concept of logical clocks, there are simple logical clocks, there are vector clocks. Two types of clocks were designed by Lampert. One was called as simple Lampert clocks, and another was called as a vector clocks. So without understanding the concepts of simple vector clocks and Lampert clocks, if you are trying to do synchronization in some other way, then I'm sorry, you will have to understand it. Then you might be stuck somewhere, or your research might be at a certain shallow level. If you combine, I'll say later on, for example, if you have a big distributed system, you want to record global state. If you want to record state of a particular system, there are certain processes running and you want to record state. All of you know there is a PCB, process control block. So PCB is written for every process, which keeps on logging, we keeps on recording everything, what is there on the stack pointer, what is there on this pointer, what are the system variable, what is the latest this particular value. So everything is recorded over there. Okay, but if there are multiple processes which are run on concurrently on many different autonomous systems, and you want to record a global state, because overall the entire system is one, you have broken down those big processes into smaller processes, P1, P2, P3, P4. Then you want to combine. So that means you want to combine, you want to take a snapshot of exactly at the same time. What was the state of process P1 on one of the system? 10:30. What is the state of another at 10 sharp 10:30, 10:30, 10:30? But as I told you, every clock is not synchronized. So it's 10:30 is different, it's 10:30 is different. So how do you take a global view? You cannot take a global view. So, but many a time there are many circumstances, there are many things, like I'll take later on garbage collection. There is some termination detection. There are many situations where we need to find out the global state of the system. So how do we record that global state of the system? This is a big challenge. Like recording global state in IoTs itself is a research problem. A lot of people are working, a lot of people have tried, a lot of people are still working. Okay, so because why do we need, if I want to record and I want to test a particular constraint, think of a simple situation. There are 20 systems, you are running a big process on these 20 systems, you have split those into P1, P2, P3, P4, and so on. But it is a logic of the same process, right? Now you want to check whether X is one variable, Y is another variable. X might be the amount which you want to withdraw from a bank. Y might be another. This thing. Just 1 second. Forgive me. Can I take a call? Just 1 second, because I'm sitting somewhere. Just 1 second. Hello. इधर ही हूँ, आप कहाँ हैं? हाँ, आप कहाँ पे? हेलो, आप कहाँ पे हैं? हेलो. हाँ जी. मैं इधर ही हूँ, मैं 10 मिनट में फ्री होने वाला हूँ. अच्छा. आप कहाँ हो? हाँ, नहीं कोई बात नहीं, आप कहाँ पे हो? तो आप मेरा 10 मिनट वेट कीजिए, मैं 10 मिनट में फ्री होने वाला हूँ, यहाँ पे बैठा हूँ डिपार्टमेंट में ना, तो मैं आपके साथ आ जाता हूँ, ठीक है?
You're not audible.
Please
Sir,
unmute
you're not
your.
audible. Please unmute yourself.
Hello.
Now you're audible.
Okay. Am I audible now? Hello.
Yes, sir. Yes, sir. You are the audible.
Okay. So how much time I've left? I suppose I'll conclude within 5 to 7 minutes. Hello.
Sir, still 20 minutes are there, sir.
Okay. No issues. Uh, so concurrency. So I was talking about. So recording global states in a distributed system is a very, very challenging task. So we need this for example, I am talking about garbage collection. I give you another example of a garbage collection. So what is a garbage collection? There are certain objects which are inactive for a very long time because they have not been pointed by some other object, and you detect a particular state of a particular process where this object is lying, and you find this particular object is passive, and you record the state of another process. There also you find out that there is no pointer pointing out to this particular object, but that invocation might be on the transit on the network, and we falsely declare as if that particular object is garbage without recording the state of the channel. So that's why I'm saying there is a very interesting thing in concurrency and recording a global state, that you will have to record the state of the channel also. Try to understand this state of the channel also, because as I told you, the delays are in terms of milliseconds. You have one process running on another machine, you have another process in a second machine. So there is a invocation which was on the transit. You recorded state of one process, you recorded state of another process, but that invocation was left unrecorded. So you might be wondering how to actually record the state of the channel. But I tell you, there are algorithms designed where we record the state of processes as well as we record the state of channel, so that you give a actual global view of the state of entire process, which is very, very important. And but with varying networks, some of the protocol which were designed one kind of network will not work for another kind of network. Try to understand it. Somebody can ask me question here, because this is very important and related to my topic of the concurrency. If I talk about concurrency, I can talk for 20 lectures on concurrency, because it's a very advanced topics, but I wanted to make it simple. I want to put it on a thought that try to understand that you have processes split, distributed over multiple autonomous machines. You can record, for example, somehow you have a magic clock. You are recording exactly at the same time the state of all processes. You combine state of all these local processes together and you form a global state. But still it is not a perfect global state, because when you were recording different processes, there might be some invocation, there might be some data which is on transit in the network and it's not recorded. So you can work upon various kind of protocols which record the state of the channel also. right? So this is a very interesting topic, and there are many issues related to concurrency, related to coordination protocol, related to voting protocols. Okay, so voting protocols, coordination protocols, concurrency protocols, a lot of work is there, a lot of challenges are there. And finally, let me come to transparency. You design a distributed system, you provide heterogeneity solution, you provide openness, you provide them all kind of scalability, fault tolerance, everything. But think of a situation, you hand this system to your client. You design the system and hand over this system to your client. And when client tried to use it, he or she has to write a command to locate a particular resource where the file is. Now the client was sitting on terminal 10, now the client is sitting on terminal 20. Now if he or she shifts her location, she will have to do something else. Now your process, your resource, like a printer, you have a LAN printer, it was located at one place, now this printer is moved to a different place. Now the user has a problem. But if you have designed your system in this manner, then definitely your system will fail. That means you have not provided the required transparency in your system. You have not provided the required transparency in your system. So providing transparency to the system is basically hiding the internal complexities of any system. To make any design, to make any system, any module, any operating system usable to the end user, it is the most important thing is the transparency. But providing transparency is not as simple. So concealing the heterogeneous and distributed nature of the system so that it appears to the user like one system. To the end user, it should appear as if it is a one system. It should not appear as if it's a distributed system. It is located at 10 different locations. To end user, it should appear as if one system. Then you can say that you have basically provided the transparency. But it has also got this transparency has also got many facets. It is very important to understand them. What are those? If you understand them, then only you can work upon transparency. A lot of work is going on transparency. Initial work, you might be understanding that initial problems in software designs were that 80%, 90% of initial design in software engineering failed. They failed because we do not, at that point of time, we did not have any standardized software engineering practices. But later on, as the software engineering became very standardized engineering processes, as you have in a mechanical engineer, electrical engineer, some test cases, some standard procedures came into place. Prior to that, most of these software projects failed due to the lack of software engineering. But later on, when this engineering came on, the most evident cause of failure, cause of non-adaptability of these softwares were basically lack of transparency. Okay, today also you think of a situation, we buy some system, we buy some process, we use certain software. If it is very user friendly, if you do not have any hassles, you do not have to bother about what is the internal inside this. If you are using it as a black box, then to the end users, this system is the most important, most most popular system, most usable system. So you have to provide different kind of transparencies to make your system very popular. First is assess transparency. What does this mean? Assess transparency. That means enables local and remote resources to be assessed using identical operations. If you are sitting on one of the systems, a printer is connected to your system. In another situation, you're sitting on a system, but that printer is not now on your system. It is located somewhere else. But the command that you are giving, Control P or anything else, for example, you are offering certain command. You need not to change your command if your local, whether it is a local resource or it is a remote resource, whether file is in your system or file is somewhere else, if you're giving identical operations, then you can say that you have basically provided the assessed transparency to your distributed system. Second one is location transparency. What is this location transparency? Enables resources to be assessed without knowledge of their location. Do not get confused. There will be another term comes. Enable resources to be assessed without knowledge of their location. Means whether resource is here, we do not need to bother. In first case, you might be having this knowledge, you might be knowing this, that the resource is whether local or resource is global, but you will give the same command. Will you give the same identical operation? But in a second case, you do not know whether your resource is local or your source is somewhere else. You are still able to assess this. Then you will say that the system has provided the location transparency. Next one is concurrency transparency. Very important. Enables several processes to cooperate concurrently using shared resources without interference between them. If you are providing a solution for concurrency, all algorithms, all scheduling algorithms, all kind of concurrent algorithms which actually provide concurrency, basically they provide concurrency transparency to the user. Manually, we do not have to dispatch a particular job or a process to one processor, then I have to wait this particular second or millisecond, then I dispatch it to the second one. No, the end user or the user of the system need not to do that. It will be done internally by the algorithm, by the logic. So we'll say that we have provided concurrency transparency. Next one is replication transparency. So that means, as I told you, in order to provide the masking, in order to provide failure masking, one of the methods that we do is the replication. You can have replicated storage. You can have a replicated some resource. You can have some replicated set of registers. But you do not have to bother about whether how they are done internally, how they are managed internally. Okay, so this all is basically provided by handled internally by the system itself. Then we say that you have provided replication transparency, right? Failure transparency enable the concurrent concealment of faults. As I told you, if you can conceal, if you can mask the faults, like I've given an example that there are failures while you are dealing with frame transmissions at the data link layer. Likewise, you have certain end-to-end failure dealt at the transport layer. And if you can, somebody can deal them in a manner that the end user need not to do anything, then you will say that it provides failure transparency. Okay. Then next is mobility transparency. Allow the movement of resources and clients within a system without affecting the operation of user or program. That means either or both. Resource can be moved, client can move while doing processing. I'm talking about while doing processing, resource is moved or the client is moving. It does not have any impact. Then you say that you have provided mobility transparency. Performance transparency. Performance transparency is the most important and very, very important kind of transparency which talks about allow the system to be reconfigured to improve performance as loads vary. What does this mean? Means this is auto reconfiguration. This is very, very important, and many people have worked on this. Many architecture, many systems have. That means you have certain set of processes, you have certain set of storages, you have certain set of logics, but your system will be configured to meet the variation, the fluctuation in the load in such a manner that automatically end result is that we get a particular amount of performance. We never go below that particular level or that particular line for as far as the performance is concerned. So we say that we have provided performance transparency. So providing performance transparency is very, very complicated, very, very tough task. Okay, so it is auto varying, auto load configuration, auto configuring the internal resources, checking the load. What is the load? If there is a fluctuation, shall I activate the new server? Shall I activate the new processor? Shall I activate something else so that the performance is always above a particular threshold? So we say that's a performance transparency. Likewise, scaling transparency. If you have understood the concept of scaling, then definitely you will understand what is scaling transparency. So scaling transparency means that allow the system and applications to expand in scale without change to the system structure or the application algorithms. That's why if you have to change entire application program, if you have to change the system structure, then you can never say that your system is scalable. But you have designed your system in such a manner that you need not to do this restructuring. Still, you add few components into your system and you are able to cater the increased load. Then you will say scaling transparency. So summing it up, your system might be very good internally, might be well designed in terms of providing fault tolerance, in terms of providing security, in terms of providing openness or other kind of things. But if you are not making it user friendly, if you are not making it transparent, your system will never be usable, right? So as far as the other things are, I think it will take a lot of time, but I'll just take little time in understanding what is the architectural model and what is the fundamental model. When we talk about a distributed system, we categorize two kind of models. One is an architectural model, another is fundamental model. So that means if we are talking about which is a client, which is a server, which is a proxy server, how they are connected, which one will change role, if it will become server or this will become client. So these kind of models, when we talk about, are architectural models. And second type of models when we talk about are basically fundamental models. So that is as good as we can be Indians, we can be Africans, we can be anything. How we look, how we interact are architectural models, how we are there. But all of us have emotions, all of us feel pain, all of us feel hunger, all of us feel those kind of things. So those things which are common in all architectural models, when we categorize them, when we put them in a different category and we try to model them, we call them as a fundamental. So clearly architectural model is component, places, parts, their interrelations. Fundamental is common properties among all these models, like failures. So you have a client server, you have a peer-to-peer or anything, failures are bound to happen. But what kind of failure? So failures have different categories. So they are further categorized into many kind of failures, right? So this way, as I told you, the middleware, just a little snapshot. You can see the right side. You have a computer and network hardware. You have operating system. On top of that, you have middleware, and then you can run your applications. The examples: RMI, group communications. It does so many things. Okay. Middleware like Sun RPC, OMG Corba, Microsoft DCOM, Java RMI. It provides building blocks for software components. Let me also explain this. Middleware services. What are different? Somebody asks you, what are middleware services? So naming means if somebody knows in one of the component, it knows by a name XYZ. So from a different process, how that process will reach there and call it, will it call it XYZ? Will it be known to that? Like, for example, scope, naming, variable names, everything that is managed by middleware services. Security, as I told you, provide all kind of security. As I told you, transactions, some transaction goes down, you are running transactions, having multiple different kind of operating system. So transaction management is also done by middleware. Persistent storage, I tell you, you can have replication, you can have a stripping, you can have a mirroring, or those kind of things, right? So event notifications and everything, right? So thank you very much. Now you can have some questions.
Thank you, sir. The house is now open for questions. Any doubt, question, answers you can ask.
Sir, as we are using the cloud computing nowadays, so in point of view, the cloud computing, how scalability and concurrency is the big problem, because most of the time we have to discuss like this issue of the security. So these two are the comes as the security issue. So how we have to solve this and how they
How you are relating security and concurrency? Security is something different. Concurrency is basically because when you say cloud, what do you understand? What is a cloud?
generally cloud is the one type of the storage that are
No,
storing in the elsewhere.
no. Cloud is not just a storage. Cloud is just everything. Cloud is storage, cloud is processing, cloud is services, cloud is software. So that's what I'm saying. We do not go to the jargon of these technologies. At the back end of your cloud, you say, what is cloud? You have a set of servers, server farm. On top of that, you have attached to that a big storage. On top of that, you are running some storage management softwares. You are running some application softwares over there. You have a storage also over there. So if I want to store some data over there, and there is a banking organization which is storing some data, some transactions from say 50 places. They are doing transaction onto a system. Say they want to store similar data at the same time on the cloud, but not from a one location. And think of a situation that time which is loaded on that particular transaction from a different 5 different or 10 different locations is different, right? So how that will be coordinated and how that will be treated at the cloud, that this is exactly data of same particular point. So without synchronization, this is not at all possible. Are you understanding? Whether it is a process or it is a storage data, or you are doing some transaction, you're accessing certain services, or you are simply storing a data. If they are not time synchronized, you will have problems. Entire thing will be wrong, right? So at the back end, at the hardware level, at the software level, there must be a synchronization. There must be a concurrency control.
Okay.
Right.
Yes.
Any other question?
Sir, you explained about the middleware very nice way, and we understood it. And can you explain the differences between software, middleware, and firmware?
Firmware or middleware.
Yeah.
See,
Yes.
firmware is something. Firmware is a kind of microprogramming that you do on a particular chip, that you do on a particular piece of hardware. Okay. When we say about the logic of say networking, logic of a middleware, some of its part could be pure in a software form. Some of the part could be embedded onto your card. What happens? Like, what do you think about the operating system nowadays? You have an operating system, right? You have a networking. Now operating system and network modules, network protocol modules are very much now sort of one package. So it is not a purely in an entire software form. It is not purely on a chip. Some logics of your network layers, like the data link layer, like the network layer, like this, or some of the logics of the operating system or the middleware, they are purely in software form. There are many of their associated layers or modules which are there on the board. If you are writing something onto the board, onto the chips, it's a firmware. So your firmware is a kind of software which you are embedding onto your these devices. But is this logic a part of your pure operating system, or is this a part of your middleware or something? Okay, so there is no clear cut that everything will be in a pure software form. So you have certain logic, but if you are asking me the difference between a firmware and a middleware, so there is no difference. These are two different things. Firmware is a technique where you are putting something on a hardware. There are two things: hardwired or firmware. So if you are
Means
microprogramming
by using transistors and other things, whatever we are programming in the chip, so that
is
we
a
call it as
hardwired.
a firmware.
You
Yes.
can do this, that's all. But that's what I'm saying. So there is a very thin line depending on different architecture. What you are putting purely in a software form, what logics you are embedding onto your chips and putting it in a firmware or a hardware. It might be hardwired, or the logic might be hardwired, it might be firmware, okay, or it might be purely in a software form. This is as good as if somebody asks you what is the difference between a driver and a controller. You have software drivers, you have controllers. So, like I'm talking about, you have a card, you have a USB to which you have a USB interface. You connect printers, you connect other devices. So you have certain logic which is fixed, which is not going to change very rapidly. You put that logic onto your card. Then also your printer can change from printer P1 to printer P2 to printer 4. These small variations are dealt by your drivers. You have software drivers because they will regularly change. You just change the software. You just change a driver. So you cannot have every time you have a new printer or something, you will have to change your board. Nothing. Okay. So the same kind of differentiation is there.
Yes.
Then okay.
Anybody else?
Okay.
Thank you, Dr. Sharma, for this nice presentation and for comprehensively taking this concurrency issues in IoTs and WSNs. If that's all, then can we just say good night, and we will meet tomorrow at 2 o'clock for the final concluding day of this faculty development program, We will be starting at 2. After we will be having 2 sessions. Then from 6:30 onwards, we will be having your test. And from 7:30 to 8, we will be having valedictory session and feedback session 2 after your test. So thank you again, Dr. Sharma.
Thank you.
Okay, good
Thank you
night
very
to all of you. Join again tomorrow for the last day of the session. Thank you.